Today we're going to reach for the stars. This electric field idea has given some of you some trouble because it's imaginary, it's make-believe, it's a gimmick, okay? And some of you are having a hard time playing make-believe. You got no imagination, people. Okay, let me see if I can spell this out for you. There are three very different concepts. There's charge, there's electric field, and there's electric force. Okay? And these are completely separate. You have to be careful when you are talking about them that you not mix and match these ideas. The charge is real. It's just extra or missing electrons. If I've got too many electrons, it's charged negatively. If I'm missing some electrons, it's charged positively. It's a characteristic of an object. An object's blue, it's round, it has a mass of 2 kilograms, and it has a charge of -3 microcoulombs. It's just a characteristic that describes that object. Now, things with mass can attract other things with mass. That characteristic can exert a force. Well, we also find that things with charge, with either too many electrons or too few electrons, can put forces on other things. Okay? But we do it through an intermediary. This imaginary field. Okay? What we say is that the field is set up by a charge. And folks, when we're looking for the field, we always look for the magnitude. And we use absolute value signs here in Coulomb's law. We never put the minus sign in here. I had a whole bunch of you in my office this morning working on homework. And you were putting the minus signs in here and trying to figure out what they meant. They don't. They don't give you any information. Okay? You just find the size of the electric field. And then, if you have a positive source, the electric field is going to be away. And if you have a negative source, the electric field is going to be towards. Okay, if you're over here, towards means to the right. If you're over here, towards means to the left. Towards means towards. Okay? You find the magnitude with that formula, and then you use this away from a positive source towards a negative source. Okay? Now, once I know the direction of the electric field, I use that to find the electric force. This is not real. The electric field is a gimmick that helps me find the force. That's a real push. That actually grabs something and tugs at it. Okay? And that force is the field if your test charge is 1. Put 1 in for your test charge and you see that they're the same thing. Okay? And that gives us an understanding of what this field is. It's a rate. It's how much force I would have if I put 1 coulomb at that location. Well, I never really put 1 coulomb there. That'd be silly. If I put half a coulomb there, I get half the force. If I put a tenth of a coulomb there, I get a tenth of the force. And here's the thing. This electric field is the force that would act on a plus 1 coulomb. And so that means if I've got an electric field to the right, and I put a positive test charge there, well, the electric field is how hard a 1 coulomb, a plus 1 coulomb would be put. If this is also a positive charge, it would be pushed the same direction. And that's what I'm ultimately looking for, that push. Now, if, on the other hand, I have an electric field to the right, and I have a negative test charge, in that case, this is going to be to the right, this is going to be a negative, and that means this force is going to be in the negative right direction, which is just another way of saying left. Okay? If a positive 1 coulomb would be pushed this way, a negative charge would be pushed the other way. Now, folks, I am asking you, I am begging you to learn 3 things. 3 things. The electric field is away from a positive source towards a negative source. That's 2 things. And then, if your test charge is negative, I have to flip the direction to get the force. That's 3 things. There's, like I said, 16 bones in the body you have to remember for biology. But here, just 3 things, and that's it. You know those 3 things? You're golden. Check to see if your neighbor knows those 3 things. Folks, this problem that you voted off the island was an old exam question, and it was a disaster. And that's why it's a good homework problem and not such a good exam problem. And the reason it was a disaster is because people got stuck right at the very start, at the get-go, and they couldn't go to part B. The first part of the problem asks them to find the electric field at that X with these 2 charges, QA and QB, in the neighborhood. Now, they went into plug-and-chug mode, and they tried to use this formula, and they knew how to use the formula, but we didn't give them QB. And so we had all sorts of people write on their paper, if you'd have done your part, I would have done my part. Now, what we did tell them, we told them that if I took a 3rd charge, QC, and I placed it at the X, it would feel no electric force. Okay, you got to keep those ideas separate. The force that it would feel electrically would be 0. Whoa! I got these 2 sources over there, and that QC doesn't even know they're there. Well, what does that tell me about the electric field? Well, if the force is just the field times the test charge, and I'm told that the force is 0, this question is really, what do I have to multiply by 4 to get 0? You can do that, okay? It's got to be 0. Now, that's what kept people hung up, high-centered for 40 minutes. Here's my message. Don't ever let yourself get high-centered during an exam for 40 minutes. Raise your hand and say, whoa, clearly I'm missing something. Because I think I need that QB. I think maybe you made a mistake in the problem. And that gives me an opportunity to smile, to wink, and say, yes, you're missing something. I did not make a mistake. I like saying that. Okay? But that would lead you to give up on that formula over there. Now, the second part of this problem asks us to find the electric field at the X due to QA alone. Magnitude and direction. Now, what about the direction? I'm just looking at QA. It's creating a field over here at the X. What's at the X?
Nothing.
Nothing. Just empty space, okay? It's just an address. Now, is the field at that location going to be to the right or to the left? To the left. It's going to be towards the negative. Towards the negative. Now, the magnitude, I can get the magnitude just from this formula here. 9 times 10 to the 9. I'm going to put 6 times 10 to the minus 9. And notice I didn't put a minus sign in there because I'm taking the absolute value. And the distance is from the source all the way over to the X. So if that's 20 centimeters and that's 10 centimeters, this would be 30 centimeters or 0.3 meters. And when I do that math, I get 600 newtons for each coulomb. That's the magnitude. Left would be the direction. Okay? Now don't say minus 600 left, because what's minus left? Right. You're right. Okay, so there's my electric field due to A. Now the total electric field is due to QA and QB combined, and it has to add up to 0. And so that means that the electric field due to B has to be 600 newtons for each coulomb to the right. What does that tell me about QB? Is it positive or negative? Positive. It's got to be positive. Now, there's 2 ways I can find out the magnitude of QB. Now, one way is to just go back into this formula and use it again. And I would say 600 is equal to K times QB. That's what I'm looking for. What distance would I use there? 0.1, because it's only 10 centimeters away from the X. And if I solve that for QB, what I find is that I get QA over 9, which is 6.7 times 10 to the minus 10 coulombs, and it's positive. Now, that's the plug and chug way. Let me show you another way. Make believe for a moment that QB has the same magnitude charge as QA. They're the same size, one's negative, one's positive. These electric fields at the X wouldn't be balanced, would they? Because B, with the same size charge, is how much closer to the X?
0.1 meters closer.
Yeah, this one is 30 centimeters. This one is 10 centimeters. It's 3 times closer. Now, because that field depends on 1 over r squared, 3 times closer is how much stronger? 9 times. 9 times. Anyone know what movie that comes from?
Yeah.
Ferris Bueller. Ferris Bueller. 9 times. Okay, never mind. Okay. Now, if the field's going to be 9 times stronger because of the distance, and I don't want that, I want the field to be the same 600 newtons per coulomb that I got from A, I'd better make the charge 9 times smaller. And that's how I get this number the easy way. See if your neighbor understood both of those ways of calculating QB. 9 times. Okay. Hey folks, just for fun, let's look at this problem that you just turned in. You have these gliders that are on a frictionless track. Each glider has a sphere attached to it. So the sphere has to stay with the glider. and we charge up these spheres, both negative, but sphere 1 has more charge, a greater magnitude of charge than sphere 2. Now, what are these gliders going to do? They're on a friction glide. Yeah, good answer. That's what gliders got to do. They got to glide. They're on a frictionless surface. The spheres that are sitting on top of them are repelling each other. They're going to fly apart. They're going to fly apart. Now we're asked to draw a free body diagram for sphere 2. If I draw that free body diagram for sphere 2, I get a gravitational force. I then ask, are there any other non-contact forces? Well, yeah, there's this electrical force by sphere 1 on sphere 2. I then ask, what touches sphere 2? Well, the glider, and the glider pushes. Whenever one thing pushes on another, there will always be a normal force. There may also be a friction force. The question is, do I need a friction force in this problem? Well, let's look at glider 2. Glider 2 has a weight force it doesn't have any electrical force on it because it's not charged. If glider 2 is pushing up on glider 2, then glider 2 must be pushing back down with a normal force. Sphere 2 is pushing down. Tick mark there, tick mark there. And the track is pushing up. But I know that glider 2 is racing to the right because these spheres are repelling each other and it's a frictionless track. And so that means that I have to have some force that's going to move that glider. And the thing that's pushing the glider is the sphere. So I'm going to have a static friction force by sphere 2 on glider 2 that's making that glider accelerate to the right. Now, if I go back to my free body diagram for S2, I have to have a third law companion. This is going to be glider 2 on S2. And I made this electrical force bigger than that friction force because this diagram for the sphere has to screen to the right. Because the sphere is speeding up to the right. Now folks, this was an exam problem. And a lot of people said, hey, the sphere is not accelerated. It never moves relative to the glider. Now you remember 205. I gave you that example of the very, very expensive sports car. $250,000. Nice leather seats. I park my butt in the leather seats, I hit the gas, and I go from 0 to 60 in 2 seconds. 2 seconds. My butt never leaves the leather seat. It is at rest with respect to the leather seat. Did my butt accelerate? Oh yeah! My butt went from 0 to 60 in 2 seconds and it felt great. That's why I paid the money. We do physics relative to the sidewalk. Okay? If glider 2 is accelerating to the right and sphere 2 is going with it, it is also accelerating to the right. And so this force has to be bigger than that force. Now, you could call this force a normal force if instead of using super glue, you use a pin and you pin it to the glider like you would a butterfly in a collection. Okay, so it depends on how you attach them. If you use super glue, you'd call it a friction force. If you use a pin, you'd call it a normal force. Now, if I do the free body diagram for sphere 1, there's going to be forces on it that I'm not going to draw, but there's going to be this electrical force by 2 on 1, and these had better be equal to each other by what law? Third law. Okay. Even though they have different size charges, they will have the same size force. Okay, are there questions on either of those problems?
If it was permanently attached, like with the pen, I mean, is there even a normal force? Because then it's a solid unit.
At that point, you start to just call them one thing. And then you draw a free body diagram for just the one unit. And internal forces we never put on our diagram. You could do it that way as well. Yeah. In this problem, because they asked us to draw the free body diagram only for S2, I chose to keep them separate conceptually. Any other questions? Okay. Last day we talked about a source charge that's spread over an extended location. In this case, the charge was smeared along a hemispherical rod. And we noticed that our formula only applies to point sources. Sources that are concentrated at a location that acts like a point. So what we did is we broke up our extended source into 9 point sources. And we were looking for the electric field at the X. Now, when homework gets turned in semester after semester, we see half of the class do it this way, and half of the class do it that way. Are both of these ways correct?
Yes.
No. We're looking for the electric field at the X. Not down here, at the X. This representation is wrong, by which I mean sick and wrong. Oh man, that's just leaves a nasty taste in my mouth. Okay. Okay. Now, who is that? Pepe Le Pew, of course it is. Okay. So, how many of you have watched Pepe Le Pew cartoons? Okay. Now, it doesn't matter how many cartoons of Pepe Le Pew you watched, because there really is only one Pepe Le Pew cartoon. There is only one plot. And you know what it is? The cat wanders into the neighborhood. Somehow the cat gets a stripe painted down her back. And then the chase is on. Pepe falls in love. And he will not take no for an answer.
Hello, chérie. All is fair in love and war, eh? I tell you what, you stop resisting me, and I will stop resisting you.
This cartoon destroyed an entire generation. Gentlemen, no means no. Pepe is an idiot. Okay? When they say no, you stop. Okay? Now, having said that, Pepe Le Pew is one of the most brilliant cartoons in terms of physics. And that's because it had a special problem that we share in physics. We never knew where Pepe was hiding. Well, the cat didn't know, but we at home knew because we could smell Pepe. Now, here's the thing. My TV doesn't stink. Your TV doesn't stink. And yet we could watch the cartoon and know exactly where Pepe was. Because the cartoonists invented lines of stink. And so suddenly you could visualize the smell. Okay? Now, we're going to use this because electric field is something that also you can't see. And so we're going to try to use these lines. We're going to borrow from Pepe Le Pew. We're going to use these lines to try to visualize the electric field. Now, you'd always see this wall, and you'd know that Pepe was behind the wall. And if you want to know exactly where Pepe is, just follow the lines to where they get close together. Okay? The closer the lines, the closer you are to the source. Okay? Now, we have a very difficult task. If we try to visualize a gravitational field, it's brutally simple. Every point in this room has a vector associated with it, pointing down 9.8 newtons per each kilogram. Deadly dull. But if I have a positive charge here and a negative charge there and another negative charge there, the electric field in the room is very robust and rich. It can be strong in this location, it can be weak over here, it can point this way at this location, it can point that way there. And so if I wanted to visualize that, one way to do it would be to put a vector at every point in space. And each of those vectors would have a different length and a different direction. And it would be crowded in here. That's not good. So what we want to do instead is we want to paint a picture that will let us see everywhere in the room where the field is strong, where it's weak, where it's pointing this way, where it's pointing that way. And that answer is lines of electric field. Very much like lines of stink. Now, lines are getting close to each other, the stink is stronger. The electric field is stronger. And what if it's a hot day? On a hot day, Pepe really stinks. And we're going to find that if I've got a big source charge, I'm going to have to represent that with more field lines. The bigger the source, charge-wise, the stronger the field near that source, and I represent a strong field, a stink, with more lines. Now, more stink means more lines. Now, if I have a single source, a spherical point source, if you will, okay? Just like that. If I have an electric field right here equal to 10, and I went out there about 5 inches, what if I went out 5 inches here? How strong would it be?
10.
It would be 10. And no matter where I went, as long as I was the same distance away, I'd always have the same strength. Now we represent strength of electric field by how close the field lines are together. Oh yeah, that's one way to represent field lines. Here's a picture of me on a bad day. Actually, it's not me, but we could be brothers. He's just losing his hair. Well, he's got a lot of hair, just not all of it. We represent the field due to a single source as being lines that are symmetric. The spacing here is always the same. And that means if I go out 5 inches here, the field lines are this close together, that gives me a certain strength of electric field. If I go out 5 inches here, I got the same spacing between the field lines, that's going to be the same strength. Now these field lines are born on positive charge and go away, and they die on negative charge and they come in and die. Now, these pictures are from the competitions book, Cutnell and Johnson, that cost $250 that you did not have to buy. And I just wanted to point out that this picture is wrong. Okay? And what's wrong about it is that they put the arrowheads at the end of the line. That makes them look like vectors. And vectors are different than field lines. Vectors, an E-field vector, only gives me the electric field at one location, at the tail of the vector. And a vector can never curve, because it's only giving me one direction. So when we're drawing field lines, we put the arrowhead in the middle of the field line to indicate that these are not vectors. Okay, so these arrowheads should have been here in the middle. They get drawn. Now, we have a representation here. Okay, they're supposed to be radially outward there. Okay. Now, this is not a real great Van de Graaff, not the best in the world, but let's see, does someone have very fine blonde hair? Look around you and look for we need a sacrifice here. It's the Hunger Games. Okay. Your village is going to have to send someone down. Okay. Okay. Whoa! This might work. That might be a little bit too much fine hair, but let's find out. Okay, up and on. Looking on your head. Hold on to that and don't let go, my friend. Now, we used to have this great big wooden block that we used to as a stand. And then one semester, a student was saying, it's shocking me, it's shocking me. I said, well, it is not, come on. What was happening is they put together that wood block out of lots of small wooden blocks with nails, and it was arcing down. She was getting, okay, shake your head a little bit there. Okay, yeah. It is fine, it's just too much of it. Okay, don't let go, don't let go. Okay, now you can let go. Okay, shorter, fine hair. Okay. That's still going to be a little bit long. You can do it? Okay. Okay. Get up there. Okay, grab on. Okay. This Van de Graaff is just not.
It is in the back a little bit.
A little bit?
Yeah.
Okay.
I can feel it.
Yeah, you can feel. Oh, there we go. There you go. On the sides here, it's coming out. Okay. Shake your head again. Okay. Okay, there we go. Okay, don't let go. Don't let go. Okay, now you can let go. Now, thank you very much. Now, the reason I say this isn't a very strong Van de Graaff is that with a good Van de Graaff, you should be able to draw an arc like about 4 inches, and I have to come in about 1 inch before it's zapping me. And okay. Now, we're going to change platforms here. I have a program that is so old, it will not run on modern operating systems that are 64-bit. So I have to bring in my old laptop. This program is called EM Fields. It was written by David Trowbridge, a friend of mine. Dave and I used to share an office in Lillian's research group. He went off to become he was in charge of all the physics animations in Microsoft's CARTA program. And so he went to work for Bill Gates. And he tried to recruit me. He invited me over and tried to get me to join his team. I went over there, it's amazing. There's food everywhere. Everyone was at Levi's, it was relaxed. But I said, no, you know, Dave, I gotta teach. I have to be a teacher. So years later, I was talking to Dave and I said, so how's your job going? I said, oh, I had to retire years ago. My stock options just went through the roof. I said, well, what do you do? I said, I just go around to elementary schools and do physics demos with them. Oh man, that's such a cool job. So I chose wrong. So this program of David's allows you to put sources. I'm going to put a -4 next to a +5. Now, this might be a +5 coulombs and a -4 coulombs, or a +5 microcoulombs and a -4 microcoulombs. It's all relative. Now, this program allows you to click anywhere, and it will give you the electric field vector. That's the field, the middle thing, the E, okay? And when I get close to the 5, it dominates because of that 1 over r squared. When I get close to the 4, it dominates because of that 1 over r squared. Now, indeed, I can take a point and just drag it around. Ooh, very large. Okay. Now, one representation would just be to click everywhere and just have these, just a bazillion of these arrows. That's not helpful. So, instead, I'm going to use directional arrows. Now, these are arrows that point in the direction of the electric field, but they're always the same length. Okay? And he's used a color coding to indicate the strength of the field, but we're going to ignore that. And with those directional arrows, I can do something interesting. If I come over here to the 5 and click, that's the direction of the electric field, radially outward. And if I march to the end of that arrow and click again, and keep doing that, I get a line that's called a line of force. Now, you're going to learn about that in next week's tutorial. Does anyone want to guess where this is going to end up? Yeah. Now, it's called a line of force because if I go back to the electric field vector, anywhere I click near that line, the electric field is going to be tangent to that line. Well, that makes sense because that's how I made the line. I asked what direction is the electric field, and I went in that direction, and I kept stepping. Now, David's program, this is the genius here, he allows the the computer to do the same thing. If I click right here, it will create a line of force. Now, you'll notice the computer got a different answer than I did. And that's because I only took steps. I took like 12 steps, and the steps were big. The computer took 1,000,000 steps, little tiny steps, and followed it along the way. So the computer's line is more accurate. Now, if I take those lines and I create a set of them, let's say I use 5 lines to represent the 5 coulombs. I should have how many lines for the -4? 4, and I'm missing one. So I go in and I put that line there. Now, that's kind of a sloppy representation. I can get a better representation by using 10 lines. Now, if I've got 10 lines for the 5, I should have 8 for the -4. I've got 1, 2, 3, 4, 5, 6, 7. I'm missing one right there. Now, what I was trying to do, I may not have been perfect at it because I'm very imperfect, but I was trying to get this spacing here the same. And clearly I didn't do a good job. But I mean, Joey, okay? Now, the reason I wanted this spacing to be the same is because close to this point charge, very close, it dominates. And if I've got a point source, the field should be radially symmetric, meaning I should get the same strength here as I do there if I'm the same distance away. Now, if I do that, if I make these symmetric around the sources, if I do a good job of that, then my field lines tell me not only the direction of the electric field, but the relative magnitude. If I go back to the vectors, where the field lines are close together, I get a big vector. Where the field lines are far apart, I get a smaller vector. Where they're really far apart, I get a teeny vector. But those vectors are always tangent to the field lines. Okay? And so these field lines paint a picture. I know it's stinky here. It's not stinky there. And I know the direction of the field. Now, questions about those field lines. On your exam, you will have a field line problem. It will be the easiest problem on the exam if you do it correctly. Okay? I'll show you in a minute. This is a summary here. The direction of the E field vector, that's this thing here. The direction is always tangent to the field line. The magnitude of the E field vector at any point is dependent on how close the lines are together, the density of field lines. When they're scrunched up together, that's stinky. That's a big field. When they're spread out, a weak field. The number of field lines leaving positive charge or entering negative charge is proportional to the size of the charge. If one charge is twice the magnitude of the other, it should have twice as many field lines connected to it. And these field lines leave positive charge and they die on negative charge. They're born on positive charge, they die on negative charge. Now, here is a representation of electric field lines. You can see that these fields are caused by a positive charge A negative charge C, and a positive charge B. You can also see, because there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 field lines, 14 field lines coming out of A, and only 5 coming out of B, that A is going to be a bigger charge by a ratio of 14 to 5. Now C has got the same number of field lines as A, so it's going to be the same size charge, but negative. Now, if I were to ask you, if I take a little positive test charge and put it at 1 and 2 and 3, what direction would the field point? A lot of people make this a hard problem by throwing away the gift. Those field lines are a gift. It took me forever on the computer to generate them. And people use them to just find out how big a charge A, B, and C are, and then they go back to their silly equation, and they make it very difficult. All they have to do is say, well, the push, it's a positive test charge, the push is in the same direction as the E field, and that's tangent to the field lines. And if I were to ask you to compare the size of those pushes at 1 and 2, again, some people, not you, but some people throw away the gift, throw away the field lines, and they say, oh, well, 1 is really, really close to 2 big charges, and 2, it's close to a big charge, but also a little charge, but maybe C is negative, so maybe that comes in. They get all confused. All they have to do is say, field lines close together, stinky. Field lines far apart, not stinky. And so the force would be bigger at 1. If I compare 2 and 3, they're closer together at 3, and so 2 would be the weakest. You see how you use those?
At point 3, since it's in between the lines, how do you know what you direct?
If it's between the lines, you look at a tangent to this line and a tangent to that line, and you take an average between those two directions. Well, they call it interpolation, but it's really just averaging. Okay? Folks, we got 2 minutes. There's one big question here. If that test charge that I was placing at 1, 2, and 3 were suddenly doubled, the size of the charge. How does that affect the force and how does that affect the field? Tell your neighbor. How does it affect the force? How does it affect the field? Okay. Here's the answer. The field is caused by A, B, and C. It is independent of the test charge. It's made by the sources. And so the E stays the same. But if the E stays the same, and I double the test charge, I double the force. So the force would double, and the field stays the same. Okay, have a great weekend.